All right, so before we get started on this lesson, I just want to make sure that we understand that this is just an introduction to average and instantaneous velocity. Average velocity, of course, you're already going to know a lot about. Instantaneous velocity is where the calculus comes in. But this is just an introduction, so it is going to be more conceptual than working out mathematical problems. So for some of you that probably not going to like that too much because we like to actually be able to work it out. But just hang with me for a little bit and know that we will get there. So let's start just by talking about average velocity. We are used to finding average velocity. It's kind of like the slope. It's the change in position over a change in time. So you go from point A to point B, and it takes this amount of time, and we divide it, and we get our average velocity. And that's really just a slope. So the average velocity is the slope of a line that joins 2 points on the graph. So if we look down here at the bottom, if this 1 and 3 are point A and point B, then we're talking about the average between these 2 points. So this average slope would be the slope of the secant line. Remember from geometry that a secant line runs through 2 points of a circle. Well, this is a portion of a curve, so it's kind of the same idea. It runs through 2 points of the curve. And that's our average velocity. Now, instantaneous velocity, that's the new concept. Instantaneous velocity is the slope of a curve at a given point. So how do we find the slope if it's supposed to be y minus y over x minus x if there's just one point? And that's where the calculus is going to come in. But for today, we're just going to say that the slope of the tangent line is our instantaneous velocity. And so visually it would look like this. If I wanted to find the slope at this point, then I want to draw a line outside my function curve so that it doesn't intersect the curve anywhere except that point. Now it's just within this section of the curve because as we know, these functions could, we could have a function that continues on up like this, and then my tangent line would go through another point on the curve. But within this little section of the curve, it is tangent to that point, or it only hits it at one point, that one given point. And so our slope of the tangent line at a given point is going to be what we're going to be calling the derivative of the function. So that's where we're headed with this. We're going to begin our concept of a derivative. So here it is. Slope of the tangent line represents the instantaneous velocity. All right, so in this example, what we're going to do are look at the slopes in this picture. They're going to ask us about the instantaneous slopes at A, B, and C, and then the secant or the average line slopes between these points. And then they also talk about the slope of 0 and the slope of 1. So we're going to compare all of these things. Average velocity of AB, which would be the slope from A to B, average velocity of BC, slope from B to C, slope from A to C, instantaneous, so it's going to be the slope of the tangent line at A, slope of the tangent line at B, slope of the tangent line at C, a slope of 0, and a slope of 1. So what I'm going to suggest is that we just go ahead and sketch all those slopes so we can see them and then just compare them, because they want us to put them in order from least to greatest. So we'll be able to see which one is the steepest to the least steep. So I'm going to go ahead and do average slopes first. I'm just going to join together points A and B. And then it asks about BC, so we'll put those together. And then it asks about AC, so we'll put that slope on here. All right, then it asks for instantaneous slope at A. So when you're drawing an instantaneous slope, it's going to be the slope of a tangent line. So it's going to go right on the outside of the curve so that your line, if it tilts too much one way or the other, it would go back through the curve. We don't want it to go back through the curve. So somewhere like this. And again, like I said, kind of conceptual. So we're just going to try to keep it in the middle of that point. The same thing at C. All right. I think we've got them all. Instantaneous at A, B, and C. Now it also talks about the number 0 or the slope of 0. So I'm just going to put that right in here somewhere so we'll remember to include it. So here's a slope of 0. And also they want us to compare this to a slope of 1. So I'll just put the slope of 1 here. Up 1 and over 1. Slope of 1. Okay, so now we just want to compare all of these. So let's go backwards because I think it'll be easier to go backwards. But as you're considering these, remember that when you get to the negative slopes, a slope of a negative that is less steep is going to be like a negative fraction. For example, this might be a slope of negative 1/2, where this would be a slope of negative 2, and negative 1/2 is smaller than negative 2. So just remember that when we get to the negative slopes. So we're going to number these backwards. I'm going to start with 8 and go back to 1. So 8 would be our biggest slope, or our most positive, steepest slope. So that would be the one right here at A. So I'm going to number that one 8. All right, then we're going to have a slope of, let's see, this one or this one. And it looks like this one might be just a little bit steeper than this one. So we're going to go with this one being 7. And then the slope of 1 is probably going to be 6. And then we've got this slope up here, the secant line at B, probably be 5. And then we've got this line running across here that's a little less than that one, so this one would probably be 4. And now we're down to the flat line straight across, slope of 0, 3. And then we're going to work our way back the other direction, so like this one would be the slope of 2, and then this one would be the least of all of those slopes because it's going to be a larger negative number. All right, so there they are. So let's see if we can find those. The average velocity of AB, that was this line right here, so I think that one was our 7. BC, that was this one right here, that was 2. AC, this one running across, was 4. Instantaneous at A, oh, y'all can't see what I'm writing. Instantaneous at A, that's this one, so that's going to be 8. Instantaneous at B, that one was up there at the top, here, so that's 5. Instantaneous at C, that was the last one, that one's going to be 1. And then our 0 was 3, and the slope of 1 was 6. All right, so like I said, this is very conceptual. These are not going to be drawn exactly the same by any of us, but just be sure when you're drawing your tangent line slopes that you try to keep them about the same distance away from the curve on either side, and it's just tangent at that point of the curve. And so now that's all we're going to be doing is comparing the slopes. Secant line slopes, tangent line slopes, average slopes, and instantaneous slopes.